Wow, just looking at this makes me angry. Okay. Okay, before we get started, does anyone have questions on the previous lecture? Is this not on right now? What is happening?
No, the structure seven.
The what?
For the structure seven.
Oh, okay, yeah.
It's so like so the parameter already modified, the part needs to be changed though. And then the rest of that was not changing remaining the share with the original unlimited reset. So the question is that will be defined by the program, you have the characteristics of this part, you check from the original which part and then for the new one, or it will be defined by the previous one.
A lot of the time it's defined by the data structure. So honestly, if this doesn't work, we might have to just view it on the laptop instead, which would be lame, but it'll work. Everybody in here has a laptop, right? Yeah. Okay. Why are we having 2 consecutive days of technical difficulties? I don't understand. Oh, that's why, because I don't have my laptop plugged in. Okay. So yeah, this when you share data between, different instances of the same data structure, like if you have the original data structure and you make your copy of it whenever you make that modification of that copy, a lot of the time the data structure is the one who manages all of that structural sharing. So one of my favorite examples of that is um so this is an immutable data structures library written in Rust. And what they do is they will use something called an atomic reference count in order to keep track of a particular node in a B tree. It will count how many references exist to that node. If there's only one reference to that node in the B tree, then it'll make modifications to the B tree because it knows that the only one who can observe those changes is the entity that's making the changes, which is fine. And so if there's more than one reference to a particular node in a B tree, then it will clone only that node and keep all the references to the children intact, and they'll remain the same. So in Rust, that's how the structural sharing works. It's something like Haskell, it's more complicated because Haskell doesn't allow data to be mutated at all. So a lot of the time what happens is you'll have something like a red-black tree, which is a balanced binary tree. And whenever you make a change to a balanced binary tree, you can't really expand it because the capacity of each node is 1. So that optimization you would have with a B tree on being able to expand and contract a single node in the B tree doesn't really matter. But that's how the structural sharing works. Are there any more questions on the things we went over last class? Because I know it was a lot. And I know it was fairly abstract. And we're going to get into the concrete examples of everything we talked about today. Okay. All right. We're going to finally start talking about Apache Spark, which is going to supply the bulk of the material in the course so far. So Spark is a large-scale data analytics platform. It's what the data science team account uses and what I use to do a huge portion of our big data stuff. We don't use it for everything that we do with big data. We have another service, a data warehouse service called Snowflake that handles a lot of our stuff. So this data warehouse, Snowflake, it stores all of our data and we can do some of our processing in Snowflake with SQL queries, but whenever we need to do something more advanced or more interactive, we go to Spark. So that's one advantage of using Spark. Another advantage of using Spark, and this is a little bit more specific to us because we use Snowflake, is that Spark is way, way cheaper than Snowflake. It's insane how much cheaper it is. Like, in order to get a single 8-core machine on Snowflake, that costs about $350 an hour. The same 8-core machine in EMR or in Spark on AWS will cost 37 cents an hour. And not only that, we have very little control over the types of instances that we use in Snowflake. Because Snowflake defines, and I read this like a year ago, so they may have updated it since then, but the last I heard is they use what's called C-type instances on AWS, which means that they have a smaller amount of memory compared to the number of cores on the machine. Now, for something like big data analytics, that can actually be a huge problem because if you're working with these big data tools in real life, one of the most persistent issues you'll see is your system will say, oops, we ran out of memory. It won't tell you why. It won't tell you, oh, it's this part of your code that's taking up so much memory, or it's this particular key or this aspect of the data that's causing your memory usage to explode. It'll just die. And a lot of the time, being able to keep all of your data in memory is more important for performance than having more cores. That's what I have found in my travels. And so Spark provides, something that Snowflake does not, both through the fact that it's like 10 times cheaper to do certain types of analytics, and because you can do all sorts of custom operations in Spark that you are not able to do in a system like Snowflake. And Snowflake is almost exclusively a SQL system. And that's useful for many different applications, but there are things that it can't do. And so Spark's programming model is a mix between a functional programming model and SQL. And I extensively use both of these things when I'm writing code in Spark. And so in Spark, you can, manage tables of data or data frames that have rows and columns, just like a SQL table does. And you can also run functional code that we discussed earlier on those SQL tables. And it's all done in a very composable way. And I'm going to show you what we did yesterday happening in Spark. So all of those functional programming patterns like map and reduce and fold, all of those things are available to you in Spark to use. And we're going to go over how to use them because they're very similar to what we did by hand yesterday. And obviously Spark runs on a distributed system, and we're going to talk about the implications of that throughout the duration of this course. But an interesting conversation that I was having with Frina before class is you don't necessarily have to use a distributed system when you're using Spark. So the data scientists at our company, what they generally do is they will take a very large machine with something like 400 gigs of memory and 96 cores and run Spark only on that machine. So it doesn't have to do any data exchange over the network between all the executors in Spark because it's running only on one machine. But if they wanted to expand their platform to multiple machines, they could do that very easily, and they wouldn't have to change any of their code to do so. So Spark is an extremely scalable system because if you weren't doing it that way, if you had a single machine and you wrote the code in such a way where you could stream in all the data from a data source and then go through it in a for loop and then, manually spawn and join threads whenever you needed to use parallelism and everything, you'd have to completely change how you wrote that code if you wanted to expand it to use multiple machines. Because then you'd have to introduce all of this extra communication between machines so you can exchange data properly. You don't have to do that in Spark. Spark will do that for you. So Spark automatically handles the communication between machines when you need to do distributed data processing. And that's what makes it so useful. And the other thing that's really nice is that the way the programming model in Spark works is it's very similar to existing functional paradigms that you would only use locally. Like if you've ever written code in JavaScript you have things like map and filter and such. Those same things exist in Spark. So Spark uses a lot of the paradigms that exist in other languages, which is what makes it so familiar to programming if you've used a functional programming language before, or have just programmed in a functional style before. And there's a huge number of languages that support functional styles now, like Python does. Python has those anonymous functions that we saw yesterday, not yesterday, Tuesday. And like Java has anonymous functions now, and Java has all these other functions that it added to those collections to support a very similar programming style than what natively exists in Apache Spark. So that's really nice. And like we talked about yesterday, programs are defined in pipelines in Spark. And so what Spark will do is it will use your code to define the data flow of the computation you need to execute. And only when you actually ask for the result, the entire computation will be executed. And we'll see a little bit later what those execution plans look like. Okay, so we have data that exists in Spark that's organized into tables, and it's almost the exact same as a regular SQL table. It has columns, and every column has its own name, and it has a bunch of rows, and these rows are not in any particular order. And that's kind of the key difference between maybe a non-distributed SQL system like MySQL or Postgres and this is in a distributed programming model, you should not treat these rows like they have any kind of order to them. And we're going to talk about why this is later on in the course, but putting data in order in a distributed context is a very, very expensive operation. It's so expensive. So if you have like a data frame of just numbers, one column of numbers, and you wanted to do a sort on those numbers, but this data frame was too large to fit on one machine, you have to do all sorts of data exchange between machines if you wanted to put the entire data set in order. It's so expensive. Like perfect example is this is conceptually similar to how Postgres does it with a B tree. And as we discussed last week, the keys in a B tree are automatically sorted. So the data will maintain the sort as you continue adding stuff to the data. And so in Snowflake, they have something called clustering. So you can cluster a SQL table on a specific column in Snowflake. And what that means is Snowflake will sort the data for you by the column it's clustered on. So if you wanted to, say, store data about a bunch of emails, and an email had multiple rows in this SQL table, you can cluster that data set by the email and group all of the rows together so you can access them all at once and don't have to scan through the entire data set in order to retrieve information on just one email. And that's really useful. But I can tell you anecdotally that if I am, writing a bunch of data to Snowflake and I don't use any clustering at all, so I'm not telling that might have been one of the other people on the call. And so if I'm writing data to Snowflake and I tell it to sort the data, then that query tends to be a lot slower. So an example is if I'm writing the results of our identity building process Do I have to mute somebody? No, I don't. Everyone on this call is muted. What is going on? Are there controls for it? Okay, thank you. So if I'm unloading the results of our data process of our, identity building process, uh, from the preliminary stage in S3 onto Snowflake where it's more permanent, if I don't tell Snowflake to cluster that data, and this is a data set of like 7 or 8 billion rows, that query will take like 5 minutes, which is great. If I do tell it to cluster, then it has to sort through all that data and exchange it and make sure that everything's partitioned correctly. It takes like 5 or 6 times longer. And that's just with the sorting, nothing else. It's not doing anything else. And that takes up like 85% of the time. Sorting is a very, very expensive operation in a distributed system. And so you'll notice, and this is part of the composability aspect of writing functional code that we talked about last time, is that almost every Spark program is composed of just four things. It's IO from data sources, as in the platform that we're using, Spark/EMR. It's all ephemeral in the sense that once you read data into Spark, you have to you do stuff with the data in Spark, you have to write it back out again. So in the infrastructure we're using in EMR, if you kill the cluster that Spark is running on, the data is gone unless you write it to an external data source. And so that's necessary to actually use any of the results of the data analytics that you're doing. And it's also necessary to even get the data for the analytics that you're going to do. So the first thing is you have to be able to write to and from your data source. And in this case, in this class, we're going to be using Amazon S3. Oh, that reminds me, by the way, did everyone get your Amazon account email? Cool. Okay. And we're probably not going to go over AWS today, but we will talk about that next week and how to set up the infrastructure and everything. And that's going to be fun. And so you have to be able to interact with your data sources. And in this case, it's writing to and from S3. Secondly, you need to be able to perform row-wise operations. And a row-wise operation is just, it's like a map that we talked about last time. It's an operation that executes itself on only a single row. And this type of operation has by far the most variety to it. Most of the operations in Spark are row-wise. Next, you have aggregations, which will take multiple rows and have some sort of combiner associated with them and combine those rows together into one. This is the reduce that we talked about last time. So like when we had the fold and we were summing things together or multiplying things together with the fold, is we are taking one element of the array and another element of the array and combining them into one. And we run that combiner over and over and over again until we only have one element left. And you can do this, these aggregations over the entire data set, or you can do it by key. And we'll talk about how that works later. And lastly, we have joins, which function exactly the same as a sequence join. Is it will build different pairs of rows when you combine two different tables together, and it will build those pairs based off of a join key or a combination of columns that you want to join on that have the same value for that join key. So to go into a little bit more detail, there are a bunch of different IO sources that you can read from and write to. You can read from and write to your local file system on your machine. And this is useful for when you just want to interact with Spark locally. You don't necessarily have to start up an EMR cluster to use Spark. If you want to just explore with the data, or maybe you don't have internet access, or maybe you don't want to spend money on an EMR cluster because we're going to have to budget ourselves when we're using AWS this semester. So if you're not ready to spend money yet on AWS, you can kind of iron things out with running Spark locally and then run them on the larger data set in EMR. So you can do that. And like I just mentioned, we can also write to and from AWS S3, which is going to be our main data store for the semester. You can also write to and from HDFS, or Hadoop Distributed File System. And HDFS is particularly useful when you're running Spark on-prem. So there's nothing preventing you from taking Spark, which is an open source project, and deploying it on all of your machines by hand and running it that way. And if you choose to do it that way, if you're running Spark on-prem, like maybe your data is on-prem and you're not allowed to put it in the cloud for compliance reasons. It happens at Equifax all the time. But so if you need to do something like that, you can use Hadoop Distributed File System to manage those data sets for you in a very nice abstracted way, in a very similar way to how S3 does it. Other questions so far? Okay. So you can also use lots of different data formats when you write to and from any data source. And Spark supports many different ones, but the main ones that we're going to be using are probably Parquet and JSON. Those are also the ones we use at Count. Parquet is particularly nice because it is a columnar format. And we'll talk about what the difference is between columnar and row-wise when we eventually talk about the differences between data warehouses and databases. JSON is not like Parquet in the sense that it's row-wise, but JSON is wonderful because the JSON schemas are flexible. So you don't need a set schema in JSON. You can just make an object. And I think the only thing that you can't do with JSON, at least something that you can't do easily, is recursive data structures. So if you needed to make like a circular singly linked list in JSON, that would be a lot more difficult because JSON is a tree structure. And one of the properties of a tree is that it's not allowed to have cycles in it. And like anything else, you can also compress your data when it's in S3 or in HDFS or even locally if you feel like it's taking up too much space. And that's especially useful with JSON because JSON, even though it's technically schemaless, a lot of the time when you write stuff to JSON, it has a lot of the same columns, right? When you have a data set, it's always, it'll have the name of that column, the name of that field, and then the value of that field. And it'll repeat the name of that field in every single row. And that is where data compression, really shines, is because data compression removes the redundancies that exist in your files that it's compressing. And a really good example of that is when we have like our machine learning omniscore model at Count. When we're done training the model, we need to serialize it so we can deserialize it and use it again somewhere else. That's how our model deployment process works. Is we will train this ML model using Spark, and then after that we will serialize the model to a giant JSON file, and then later we will upload it to our web servers and deploy it to production so that customers can use this AI model. And that AI model is actually just serialized as JSON. And when the JSON is not compressed, it takes up like a gigabyte of storage. When it is compressed, it takes up 20 megabytes. It's a 50x decrease from compression. Now I know that sounds impressive because you're like, oh wow, compression's really effective. No. It's just because JSON is that inefficient. But but JSON is also one of my favorite serialization formats because of how flexible it is. And because it's readable. I can read it, and I love it for that. And compression will take away a lot of its weaknesses, which is nice. Any questions on that? Okay. So Spark has, oh yeah.
So this, you might have your formats. These are like file, like you're not listing, like database tables, like data tables. Like I expect it. If you're not, can. That's not like that to like that's secret input to you're saying that I always have to read that file into Sparks data that never is it.
So that connectivity does exist. I've never used it. Maybe I can do some research and we can go over how to do it later in the semester, but I've never used it. And so my primary familiarity is doing stuff and interfacing between Spark and S3 using just files like this. But Spark does have database connectivity available to it. And you can read stuff from databases in the same way that you'd be able to read a SQL table. In fact, Spark has its own data warehouse infrastructure called Hub. So Hive is a kind of on-prem data warehouse that you can use in the absence of, other commercial options. And you can control basically everything that happens with Hive Data Warehouse because you're the one running it.
On-prem is not in the cloud, Hive is not in the cloud.
Well, you can run Hive in the well, everything you can run on-prem, you can run in the cloud, but you'd have to manage it yourself. So Spark has was that all? Okay, cool. So Spark also has a lot of the a lot of the data types that you would have access to in almost any programming language. You have signed integers. It doesn't have unsigned integers, which is really annoying. It's especially annoying because 90% of the integers that I use are unsigned. I don't know why signed is the default. It makes no sense to me, but whatever. So all of the integers are signed. It has all of your standard sizes, 8, 16, 32, and 64-bit integers. It has Booleans, floats, strings. It also has uh, larger data structures as column types. So you can use an array as a column type and a map as a column type, which is cool. And I have used both of those before many times as columns in Spark. And you can also build custom structs. You can have custom data types in Spark. And that's really cool because you can combine these custom data types and these other data types in almost every way imaginable. So you can have an individual column that's just a struct with a bunch of simple fields. You can have a map whose keys are a struct type. You can have a struct whose fields are a map type or an array type or whichever. You can have a map whose values are array types, arrays of structs, or whichever you want. You can combine them in almost any way you want. So when you mix all these together, you get a very powerful type system, deceptively so. It's like with JSON, where JSON only has like 7 different types available to it, right? It has number, Boolean, string, object, array, what am I missing? Null. I think that's all. But from those 6 types, you can build pretty much anything out of that. And it's the same thing over here. No, they're kind of just called different things in different places. Sometimes they will get more specific on how the map is implemented. So you'll see something like a hash map or a tree map. And the Python dictionary is kind of mute on that. It doesn't tell you it doesn't explicitly tell you what kind of map it is, but we know it's a hash table because it uses that built-in Python hash function in order to calculate where it should store the value. And so it's not going to allow you to store any non-hashable object in there. So we got a pretty good idea that the Python dictionary is just a hash table. But yes, maps directly correspond to Python dictionaries in Spark because we're going to talk about this later, but you can write UDFs in Python to use in Spark. So it's not just the built-in functions that are available to you in Spark. You can use Python UDFs. And when Spark does its data munging between what it has, the format that it has natively, and the data format that Python expects, when it does that translation, it turns the Spark map type into a Python dictionary. Make sense? Okay. What's next? You know, I feel like just doing a demonstration right now. Do we want to just get into the code? That sounds fun. Let's do that. Okay. So we can import Spark just like any other library. Okay. And so then we have to start up what's called a Spark session. So I'm just going to call my Spark session Spark. And that is spark.sql.spark session builder dot we're going to name this. Can everyone see? Is this big enough? Huh? Is that good? Okay. So we're going to call this Spark example. And then we're going to create the set. Oh, no, we have to specify that we're going to make this particular session local. So it's not going to connect to any external EMR cluster. It's just running on this machine. Using existing Spark session. Oh, I already started it. I should restart. Let's do that again. Okay. So now we can, yeah.
So effectively for the PySpark, so you can write Spark like any minute or different terms, the PySpark and the Python Spark.
You can't use any language. That's actually a really interesting question because Spark is written in Scala. I wrote part of my master's project in Scala, and I thought it was a great language, but now I hate it because of how complex the language is. Scala is kind of an alternative version of Java, so it's a JVM language. It runs on the JVM and it compiles to Java bytecode. And the code that's written in Scala is what's the word I'm looking for? Interoperable with Java. So you can use Scala code in Java programs and you can use Java code in Scala programs. And it shares all of these properties with Kotlin. And what Scala was designed to do is take Java and give a kind of a more functional twist to it. So Scala has a lot more native support for functional programming than Java does. Java has done a lot to catch up to the features of Scala in recent years. And Scala also wanted, to experiment with all these other ideas that Java kind of screwed up, like the fact that you can assign any object in Java to a null pointer is a huge problem. And so what Scala decided to do was they were like, okay, you cannot assign anything to the null value unless you explicitly declare it null. You declare it nullable using this option type in Scala that gives you this selector between the value existing and the value not, which would have been a great solution, except the fact that you can't assign something to null is a convention in Scala and not anything enforced by the compiler or the runtime. So it's basically chaos and you can do whatever you want, except and the only thing preventing you from doing it is the Scala documentation telling you not to. I realized I was ranting. I'm sorry. But anyway, Spark is written in Scala, and that's the primary language. And this class used to be taught in Java/Scala, but I know that most data scientists will be using Python in their analytics, which is why I decided to teach it in Python instead. And we use PySpark at Count instead of Spark written in Scala. And so Spark has those two primary versions, with the one written in Scala or the JVM for the JVM languages and the one written in Python. Spark 4.0 is weird because it's trying to make what's called Spark Connect available to a bunch of different languages. But Spark Connect is very different from using Spark this way, the way we're doing it in class, because Spark Connect, they have Spark Connect for Go and Rust and all these other languages, but the key difference is that you can't have UDFs in those other languages. Because UDFs are quite a complex feature, right? Spark is written in Scala, but you can run Java code or you can run Python code. And the reason that gets so complicated is because on every Spark executor, if you want to run Python code, since it's written in Java, you have to start up this external Python instance somewhere and then send the data to Python, do the processing in Python, and then send the data back. So you have to do all this translation between Spark and Java. And every time you add a new language, you have to add a new translation somewhere. So adding new language support where you can have UDFs is non-trivial. And so Spark Connect still, at least theoretically, it's in the preview stages right now, but Spark Connect will still theoretically allow languages like Golang and Rust to connect to Spark and use built-in Spark functionality. So everything that's not UDFs, you can do in Spark with something like Rust or Golang. But outside of that, you would have to use Python or Scala or Java. Does that answer the question? Okay. Okay. So now we can create our data set, or we can read our data set. And I'm going to say is the complete works of William Shakespeare. So we can use spark.read.text. And because these are just normal text files, and it'll read these text files in line by line. And we are going to read it from this directory here. Whoops. Paste it in the other place. Okay. And so then what we're going to do is, so this method right here creates a data frame. And what we're going to do is we're not going to assign that data frame to a variable. What I usually like to do instead is I like to store these data frames in tables. So we're going to create or replace temp u. And you can make aliases for this kind of thing, and I can teach you how to do that later. So we don't have to constantly type this massive thing every time. We're just going to call it will. Okay. So there we go. All right. So we've defined that table. And if we look at, we can do spark.sql show tables.
Hey, Professor, I just want to say, are you sharing your screen, coding screen? We are just seeing the slides.
Oh, really? You're just seeing the slides?
Yeah.
Okay. Can you see
Yeah.
it now?
Yes. Thank you.
Okay, perfect. Okay. So now we've created this new table named Will, and it's a temporary table. And so we can also look at the contents of that table. Start that table. Will show. And I'm going to say truncate equals false. And what truncate means is it will usually just take every column and take the first, if it's a string, it'll take like the first few characters of that string, and then it'll just kind of trail off, dot, dot, dot. What truncate equals false tells it to do is it tells it to show the entire string no matter how long it is. So do not truncate the string when you display it. And here we go. So there's only one column, which is value, which makes sense because we're only reading in plain text files, and we never gave it a column value at all, but we can create new columns. So if we want to create new columns, what do you mean where?
How would know on recurring basis? How does it know that? Is it still missing memory?
So that depends. When you create a table in Spark, you can specify where that table is going to be persisted. By default, the table is going to be partially cached in memory, but when you need to evict that memory to make room for something else, it'll go away, and you have to recalculate the whole thing.
The table is just in line. How does it really do?
It's not. I'm just giving these name tables that are managed in a different way. That's all.
Okay.
So it's still all data frames under the hood. They're just being treated like SQL tables. That's the only difference. And so what this spark.table method does is it will take the name of the table you give it and then return a data frame that refers to that table. So yeah, so these data frames and tables are interchangeable. So you can use data frames to refer to tables, and you can turn data frames into tables and so on. So they're the same thing. So the data frame just represents access to a table. That's all. So we can add a column. What do we want to add as a column? Line count? Well, every line is its own row. So per row, that would just be a line count of 1 at a time.
What,
Character count. Okay. So we can add a column. We can say with column. The name of the column is going to be line length. And you'll need to refer to a PySpark function to get the length of the column. So we'll do PySpark.sql dot functions dot length. I think that's what it is. I have to look everything up every time I program in Spark because I forget the names of everything. And we're going to get the length of the value column. Actually, what I should do is I should create an alias for that. Okay. So now we can look at that and we can say, okay, so we have 2 columns. One is still just the line of text, and the other is the length of that line. And so we've added that column to this resulting data frame. But what you'll also notice is that every time you call a method on one of these data frames, it returns a new data frame. So if we just looked at the will table again with that data straight from the files without making any changes, we'll see that it hasn't changed. So the length column isn't there. So this is what I meant when I was talking about immutable data last time, is these data frames, once you create them, don't change unless you delete them and then recreate them again with the same name. So the will table is exactly the same. And this data frame isn't actually saved anywhere. We can save it in a plate. We can save it and add it as a different table. So we can say will with length. What just happened? Oh, I know the problem is that needs to be capitalized. Okay, so now we have two tables running around in there. So we have will, and we have will with. Okay, so let's do something else now. What if we wanted to count how many times each word occurs in this data set in the entire works of William Shakespeare? How would we do that? What do we need to do? Yes. Yes. So how can we split up our words? Well, what we can do is we can say column words and I forget the name. Let's look. This is the PySpark documentation, by the way. You can look at the API reference and it'll give you all the functions that are available to you. It occurs to me now that it's too small to see. Better? Yeah. Everybody see? Cool. Okay. So we'll look at the functions and did it change how it's rendered because it's too small? There it is. Okay. So we have this list of functions that's available to us. We can go down to time functions. No. Holy mackerel, this is a lot of functions. Okay. Partition, aggregate, yappity, 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 yap. Okay, let's search for split. That's what we want. All right, there we go. So it splits the string. And let's just make sure this does what we want. Split string around max G's of a given column. And returns an array of separated strings. Which is exactly what we want. Okay. And so we can read f.split. The first argument, the column. Yes. Okay. Column. This is how you would refer to a column just in vanilla Spark. You can also do a SQL expression, which I'll do in a second. Value. And then our pattern is going to be or we probably want to split on all white space. Yeah. Okay. So now we can show that and see where that gets us. Okay, there we go. So that gives us an array by William Shakespeare, Hamlet, edited by blah, blah, blah. Oh, wait, that's a problem. So if there are multiple spaces, it'll still split each space individually. That's not good. So we'll do that. And this is a regular expression. And what that will do is it will take any number of spaces and match that pattern and then split on that instead of just on one space. So let's see if that gives us what we want. Still no. So then we would have to do something like, how do we filter this kind of thing out? So now that we have this array, how do we filter that out? Well, so what we can do first is we don't need the value column anymore, so we can drop the column. And then what we can do is we can say dot select f dot call words. We can do f dot. Actually, let's look at just this to see what it looks like. Okay, so now we only have the words column, which is this array. Now what we can do is we can say dot select f dot explode. Can anyone tell me what explode does? Yeah, it separates each element out in the array into its own row. So if we don't, so let's say we don't drop, this value part. What this is going to do, still dropped. Why? Oh, it's because I wasn't selecting value. Okay, so you can see what the explode did was it took, actually, let's also select the words column just so we can see the contrast here. Okay, so we can see the value in the words column remain unchanged, but now there's a new copy of every one of these rows for every element in the words array. So there's by, and the entire row would have been by William Shakespeare. There's William, and the entire row is by William Shakespeare. And there's Shakespeare, and the entire row is by William Shakespeare. So the explode function will take the array column that you give as an argument, and then generate a new row in the resultant data frame for every value in that array. And it'll make copies of every other column. Make sense? Good. Okay. So we don't need that anymore. We can just have the words. Okay. So now we've noticed that, all right, there's this empty string in here. How can we deal with that? So that's not, an empty string isn't a word. So how do we deal with it? Huh? Drop? Yeah, how do we drop them? So the drop function is for columns. So how do we drop rows? Hmm? Yeah, so how we do this is very similar to how we would do it in SQL, except instead of a select where, we can use either the filter function or the where function. So I usually use filter because that's what most functional programming languages use. So we can do filter, and filter is positive. So it'll match every row for which that condition is true, and then it will only include the rows for which that condition is true in the resultant data frame. So we can say filter, we're going to have to call of word is not equal to the empty string. And we'll see what that gets us. No more empty string. There we go. Okay. So, so what the split function does is it takes the value you're splitting on, so the delimiter. In this case, the delimiter is a regular expression pattern, and it will use that to separate different parts of the string, but it will not include them in. Yes. Well, we solved that problem by adding this plus. So what the plus does is it matches one or more instances of the white space. So we wound up with an empty string because one of the lines in the original data frame started with a space. So it separated the empty string, which is what was before the space, and then the guy's name, which is what was after the space. So it still kept the empty string. And so we needed to filter it out this way. So now what we need to do is we have punctuation in here, which probably isn't what we want. So how can we get rid of the punctuation? So we could do it with filter, but then that would remove the entire row. Yeah, filter removes the entire row. So it doesn't change the rows. So yeah, we can say, we can do another select. And so select in this context is equivalent to map that we were discussing earlier. So we can have select, and we would need to dot. We wouldn't want split. We would want regex replace. And so what this does is this finds matches for every occurrence of the pattern in the string, and then replaces it with whatever we tell it to replace it with. So what we want is replace, and then we have what column are we looking for? Word. And then R. So what we want to filter out is everything that is not a letter, basically. So we want to keep, so what this caret symbol means in regular expression syntax is not, so it's a negation. So if it's not A to Z uppercase or A to Z lowercase, it's neither of those two things, we're going to replace that with the empty string. So now, and then we're going to name the column. So I have enough space. All right. So now we remove that, which is great. And so you'll notice that select, it excludes every column that you didn't explicitly include in here. So if we did a with column instead of a select, and we named this new word, we deleted this, then that would keep both. So we have the original word without this munging over here, this replacing, and we have the newer one with the munging. So that's the difference between with column and select. So with column just adds another column onto the data frame, and select removes all of the columns except for the ones that you specify in the select statement. So it's just like SQL in that way. And the fact that SQL doesn't have with column is disappointing, but so you have to select all the columns every time you want to do something with SQL. I don't know if I'm the only one annoyed by that, but
I think it only showing us what it's what it's picking on, picking value, picking value.
oh, that's just the default. So we can tell it to give us more. What just happened? Parameter new word cannot be resolved. Oh, that's why. Because new word doesn't exist yet. So we can tell it to do as much as we want. So yeah, it took the HTTPS :// and removed the ://. I did not know there would be a link in here, but that's an interesting example of what happens. Oh, and this is interesting. So this line was entirely characters that were stripped out. So now it's an empty string. So what do we do to fix this problem?
Filter down below.
Yeah. So we want to filter after we do this, replacement. Now let's see where that gets us. What just happened? Oh, we're not filtering on the right column. Sweet. I don't see it. Okay. And it's getting rid of the commas, and the periods. That's good. Okay. And when I'm doing my work, just when I'm doing science or engineering, this is how I check my work. This is how a lot of the data scientists check their work. Uh, when they're building prototypes is just spot checking. Because a lot of the time we don't have actual data to verify what we're doing. That's a big problem in our identity building process, is that we can, build these identities and cluster different parts of the graph together. We have no idea if what we were doing is actually correct, because we don't have a source of truth. Because in order to do that, we would need somebody telling us that, hey, the fact that you group these things together is the right grouping, or no, this grouping is wrong. And the only way we know the difference is if we personally go in and check. And we know because we know the person whose information we're looking up. We're usually just looking up ourselves to see if it grouped our data correctly in there. And that's all we can do. Because if we had a source of truth, we wouldn't even need an identity building process in the first place, because we would just have that information. It's that fundamental problem in data science where every time you have to do something non-trivial, you're like, oh, crap, I don't have any actual supervised examples to work off of. Guess I just have to guess. All right. So we got this now. So what I also want to do is I want to make this case insensitive. So I also want everything to be lowercase. So we can do that too. So now we can look at the new word and everything looks great. So now, how do we actually count the occurrences of each word? And it's exactly how you would do it in SQL. Yeah. So with an aggregate function, what's the syntax for it in SQL? Huh? Yeah. So we would use count. What kind of clause would we use in SQL? Huh? Over what? Over what key? Oh, I see what you mean. So we want to see how many times each word occurs. We don't want to see how many unique words there are. So we want to see I want how many times we see each word in the data set. Yeah. So we need to group by new word. And then we aggregate, and the only thing we want is the count. And we're just going to call that frequency. So then we can do something like that. Hello? Oh, there we go. Oh, apparently the word art appears almost 1,000 times. That's interesting. So then, if we want to see what the most common word is, what can we do?
You can sort the one at the same time, and then we show the 100, then we just make a 100 sort. You have, with the, when we sort that we should be.
So you could,
So I don't wanna wait, you can think about how long it takes to sort, let's say I get on a million records, I'm gonna wanna sort them, but I don't wanna wait. I just wanna see if it's good.
yeah.
How could I just sort it? Yeah, please.
So we could try doing something like dot limit, and we could limit it to 10 rows. So that would take, only a subset of the data. We'll take 10 rows. And then we do an order by.
First, once I limit it first.
Yeah.
Oh,
So as long as you limit it first, then you can tell it's going to work. And then so you can order by the frequency. What just happened? So no object order by. Is this a capitalization issue? Is it this? Yeah, it is. Okay. Oh, wait. That did it in the opposite direction we wanted it to. So how do we flip that? Huh? Yeah. So we need to specify descending order. So we do it with f dot descending. And we can do it that way. Great. But that's not all the data. So, and because this is such a small data set, we can order the entire thing. And what a surprise, the is the most common word. Good to know. So let's say this data set was like way bigger. This data set was way bigger and it was really hard to sort all these things. How could we find just the maximum word without having to sort anything? Not interested in the second most common or the third most common or anything like that. Just the most common. How do we do that? Let's say we didn't want to sort it because that's a pain and it takes a while. Hmm? Yes. So it finds the maximum number. What if we also want the word? So we want the number of times that, most common word occurred, and we also want what word that is. So we would use the max function, but we need to do something else in order to also get the word. Yeah. So I would not use a window because that also involves sorting. So what we could do, and Spark might optimize it because it'll be like, okay, you're asking for a window, but you're only looking for the top row, so I'll just go ahead and find the maximum anyway. I do not trust Spark's optimizer. I've used Spark enough to know to not trust its optimizer to do the right thing because it's stupid. Well, what we can do is we can aggregate again, and we can say dot aggregate. So there are two dot aggregates in a row here. What the first dot aggregate is doing is after the group by, it'll aggregate everything by the key that you grouped by. The second aggregate doesn't have any group by associated with it, so it'll aggregate over the entire data set. So what we can do here is okay, is we can say f dot max, and then Spark has this very interesting property with how it sorts structs. So what you can do with a struct is, I'm just going to do an f dot expression with this because it's just easier that way. Max of struct frequency, new word, and that should get us where we need to go. So what it does is, the default sorting behavior in Spark is that when you have a struct, it'll sort lexicographically by the first element of that, or the first field of that struct. And then if those two values in the first field are the same, it'll sort secondarily by the next field. So it will look at that. All right. So this gave us exactly what we wanted. It didn't sort them. It took the maximum, which is very different because of how the data is managed during that aggregation. The data is managed during the aggregation very differently in a max than it is in a sort. It's much more efficient when you're doing a max because you don't actually have to do basically any data shuffling at all. What happens when you're doing a max is that the data is split up into a bunch of different machines when you're using Spark, right? So what you can do is, when you're just looking for the max, is you can find the maximum of every individual machine. And once you do that, since you only have like 100 machines, you can send those 100 values up to the coordinator, and the coordinator finds the maximum value of those 100 values. And it's not very much because it's only 100 values. And then it can find the maximum of everything over there. So it's much more efficient that way because the only data that's being exchanged is the single row from every machine. You don't have to do any other data exchange beyond that. So that's what makes it so fast. And I've used this technique too to make finding maximums faster. It's fun.
Are you going to finish this code too?
I can. All right. If there are no questions, we're done. All right, we're done. See you all next week.